So far, we've talked about charges moving in magnetic fields, so it seems a very reasonable thing to then imagine that we put a wire in a magnetic field carrying some current I, right? I mean, current is after all charge in motion, so it seems like a very natural step. And so that's exactly what we're going to talk about today. So let's imagine that I have a wire. Here's a close-up view of my wire. Has some length, call it L. And let's say that I've placed it, or let's say that my current, so this is just sort of a portion of my wire, and through this wire I have a current I flowing from left to right, say. And let's say that I put this wire in an external magnetic field that points straight up. A uniform external magnetic field. So I'll call this B external. Okay? By the way, this is not the magnetic field that the wire itself created. We talked about that too. A wire carrying current is going to set up its own magnetic field, but that's not the magnetic field that I'm drawing here. Right? If you like, you can say that the magnetic field that the wire sets up is very weak compared to this really strong magnetic field that I put the wire in, although it actually need not be. But that's one way to think about it. Okay, and the question is, what's going to happen to the wire? Well, in fact, you've already seen this. I showed you this last time. I have charges moving to the right, which means, and current I, you can think of the flow of, you can think of as the flow of positive charge. So if I have charges moving to the right in an external magnetic field, use your handy right hand rule number 2. Put your fingers in the direction of that motion. Orient your hand so that you can curl your fingers in the direction of the magnetic field, and then your thumb tells you the direction of the force. So this wire is going to feel a force towards you. Now, what is the magnitude of that force going to be? Well, that's not as easy, right? I mean, we know a formula for the force felt by a charge and moving in a magnetic field. It's QVB sine theta, right? How do we adapt that formula to work for a wire? Well, again, you can think of the current in a wire as being carried by a bunch of little point charges that are sort of zipping around and making their way down the conductor, right? So again, I can think of current as electrons moving this way or as little positive charges moving to the right. So for simplicity, let me just imagine that my wire has a bunch of little positive charges that are making their way slowly down the length of the wire with some speed. We know what that speed is. It's called V sub d. The drift velocity, right? An electron, on average, is going to make it down the length of the wire with some drift velocity, which can be on the order of 10 to the minus 3 meters per second, something along those lines, right? So we can first of all calculate the time required for one of these charges to make it from point A, say, to point B down the length of this wire. That time would be the length of the wire divided by this average drift velocity. Now, another thing is we can calculate, we know that current is delta Q over delta T. It's the amount of charge passing by a fixed point in space divided by the time interval. So I could modify this a little bit to calculate delta Q. Delta Q you can think of as the amount of charge passing a fixed point on this wire in some time interval delta T. That would be I times delta T from this formula right here. But we actually already know that that's I times L divided by VD. Okay? So where am I going with this? Well, if this is the amount of charge that's moving to the right here with speed VD, then I can immediately calculate what the force on that charge would be. The magnetic force, the magnitude of that magnetic force, we already know that the direction is going to be out towards you, but the magnitude, FB, is going to be QV B times the sine of theta, where in this particular example, my Q is just this delta Q. My V would be VD. My B is just whatever the external field is. And in this case, the angle between the magnetic field and the direction of motion is just is 90 degrees in this particular example. So sine of 90 is 1. I'm going to go ahead and keep the sign here, just so I can make this as general as possible. Okay, so let me plug this into here. You can see that the v sub d's cancel. Turns out it doesn't actually matter what the drift velocity is in this wire. It only matters what the force is. So this would be I L B times the sine of theta. Now I'm going to put a circle around this, because what we've just done is calculated the magnitude of the force on a length of wire sitting in an external magnetic field carrying current I, where theta is the angle between the current and the magnetic field. So now we've got all possible bases covered. I can calculate lots of different forces for lots of different scenarios using this formula. And what about the direction? Well, you would just use right-hand rule number 2, as I mentioned before. So we're going to see lots of different examples of problems like this, where we put wires in magnetic fields and just try to figure out what happens. A cool example involves actually a current loop. Okay? So let's imagine I put a current loop in an external magnetic field. So I'll just, for convenience, make my loop kind of rectangular like this. So these are the wires of my loop. Now, attached to this loop of wire, I haven't drawn it, but attached to this loop of wire must be some sort of battery, not pictured here, which is causing a current to flow, say, this way, counterclockwise. So let's say I have a counterclockwise current I flowing through my loop. Let's say that I've got, let's just say that the width of my loop is W, the height of my loop is L, and the magnetic field that I have in this region, I don't know, maybe it points up. Again, this is an external magnetic field. Okay, so let's think about for a minute what's going to happen to this loop. And let's try to calculate what's going to happen to this loop. Well, I've got 4 different little wire segments, 4 lengths of wire. Let me label them. I'll call this one 1, 2, 3, and 4. And let's just calculate what's going to happen to each one of those wire segments in turn. For starters, let's look at wire segment 1. That has a current that points down and a magnetic field that points up. Those are in opposite directions, so the angle theta in our force formula would be 180 degrees, but the sine of 180 degrees is 0. So there's no force on wire segment 1. So the force on wire segment 1 is 0. And by an exactly similar argument, I can say that there's no force on wire segment 3 either, since theta for wire 3 would be 0. And so there is a force, however, on wire segments 2 and 4. Number 2, well, I have a length of wire, length W, in a magnetic field, and the angle between them is 90 degrees. The sine of 90 degrees is 1, and so F2 would be I times W times B. That's just ILB sine theta, right? Where sine theta gave me 1 because theta was 90. So IWB. Now what's the direction of that force? Well, right-hand rule number 2, current is this way. Put your fingers in the direction of current. Now I turn my hand so that I can curl my fingers in the direction of B external. That points my thumb into the page. And so this force is going to be into the page. So this wire is going to be pushed that way. And what about F3? Well, again, it's going to be IWB for the same reasons that it was up here, but now the direction is going to be flipped. In this case, the force direction is out of the page. So that's kind of interesting. We have nothing happening here because the forces are 0 for 1 and 3, but here I have, at location 2, I have a push, and at location 4, I have a pull. 1 second. Okay, so here's kind of a model of what I have here, right? So basically what I said is that on this wire, I've got a force that's away from you, and on this wire, I have a force towards you. So if I were to just let this thing go, then it's going to rotate like that, right? It's going to rotate with the bottom coming towards you, and it's going to go like that. So it's going to feel not a net force, right? Because these two forces are equal and opposite in magnitude. So there's no net force, but there is a net torque. It's a torque that causes things to rotate. So, as I just illustrated, the axis about which this thing is then going to rotate would be a line that sort of cuts the L through the center, and the whole thing is going to start, let's see, into the page, yeah, so it's going to go like that. And what's the magnitude of that torque going to be? Well, torque, if you recall, is R times F times the sine of theta, right? This is from 105, where R is the distance away from the rotation axis at which this force is applied, and theta is the angle between R and F. Well, how would that work in this situation? Well, R in this case would just be the distance between the rotation axis and wire 2, or wire 4, which in this case is just L over 2. And since the distance between the rotation axis and the wire 2 or 4 is up or down, and the force is either into the page or out of the page, this sine theta is once again 90 degrees. And so what I wind up with, for example, the torque on wire segment 2 would then be R times, or excuse me, L over 2 times IWB times the sine of 90 degrees, right? And which way? Well, if I'm looking from this side, so if my eye is over here and I'm looking in this direction, then the whole thing is going to appear to rotate counterclockwise. So that would say that that's counterclockwise torque from the left. It's a counterclockwise torque from the left. And then the torque on wire segment 4 is going to be exactly equal in magnitude, L over 2 times IWB. And that's also going to be counterclockwise, because again, both of these torques are trying to initiate this counterclockwise rotation. So again, counterclockwise from left. And so what is the net torque? Well, the net torque on this loop, the net torque, which is the vector sum of all of the other torques, is just going to be L over 2 plus L over 2, which is just L times IWB. So IWLB. If I put that in parentheses, you'll notice that W times L is just the area of the loop. So another way to write this is I times A times B. So that's kind of a useful expression for the torque felt by a loop that's free to rotate about an axis that passes through its center, sitting in the same plane as an external magnetic field. That was a lot of words, so you probably want to go back and listen to that again, because this formula will change depending on some other considerations. But in this example, what I just said was true. Okay. I'll show you in class, by the way, how you can build a motor based on this principle.